seminar. So this is a series of 4 seminars that are taking place this semester, where we're hearing from students, postdocs, and faculty from the community. So for today's seminar, we'll be hearing from 2 students in the community. So the format will be, we'll have 2 30-minute slots. And so hopefully we can save all the questions for the end of each of those slots. So first up, we have Zhaoyong Liu. Zhaoyong received his BE degree in automatic control from Nanjing University of Science and Technology in 2019. He's currently working towards his PhD in control science and engineering from the School of Automation at the same university. He's now under the supervision of Professor Haoping Wang. He has also been a visiting student at the University of L'Aquila for the past year, working with co-supervisor Professor Elena DeSantis. His current research interests include switch systems, observability, sample data observers, and adaptive observers. So without any further ado, Zhaoyong, the floor is yours.
Okay, thank you. Thank you, Akash, and thank you for introducing. Okay, so today, my topic is about event-triggered data estimation for network switch systems and with an output predictor approach. And these 2 authors are my supervisors, and these 2 other authors are my cooperators, and they are from NJUST and IPM Mexico City. Okay, so first I will give you the introduction of the motivation of this work, and then I will introduce you some related work. And in the third part, I will introduce you the research contents in this work. And then I will show you the theoretical and the simulation results. Finally, I will show the conclusion and introduce some ongoing works that we are doing now. So first, what is switch systems? Actually, many practical systems, they exhibit multiple mode switch behaviors. For example, here in the multi-agent formation, there may be several topologies in the multi-agent formation, and the formation may switch between these several topologies. So it means that single system mode is not enough to handle this kind of problems. So it's necessary to model these kind of systems as switch systems. And also on the other hand, with the development of digitalization and networking technology, network control systems is very widely used. So networked switch systems means that the plant can be modeled as switch systems, and the sensor and the observer, they are spatially distributed. So first, the sensor will measure the output of the system, and then it will be sampled and transmitted through the network to the remote observer. And the observer will use the input and the sampled output to estimate the continuous state. However, some networked induced phenomena arise unavoidably, such as aperiodic sampling, quantization, transmission delay, packet loss, and cyber attacks. And here we mainly focus on the aperiodic sampling phenomenon and the transmission delay phenomenon. So in this case, traditional state observers for continuous time or discrete time switch systems are no longer applicable. So to deal with this problem, some data observer should be used. Basically, there are 3 main structures of the some data observer. So the first structure is called the zero-order hold observer. Its basic idea is that the most recent summed output is used to correct the observation or estimation error. And it's in a zero-order hold type. And the second structure is called continuous discrete observer, which means it's hybrid. or we can call it impulsive observer. Actually, it equals to a state predictor and an impulsive corrector. The state predictor means that we can use the system dynamics to predict the system state during the sampling instance, because during the sampling instance, no summed output is accessible. So we can just predict. And at each time the new summed output is accessible, we can use impulsive corrector to correct the prediction. So that's the basic idea. The third structure is called output predictor. So the difference between the second one and third one is that in the second one, we predict the system state directly, and we correct it at sampling instant. So it means that at each sampling time, the estimate state is not continuous. But for the third one, we just predict the output instead of the state directly, and the output predictor will be reset with new summed output. So that's the basic idea of these three kinds of sum state observer. And also in this paper, it unifies all these kinds of sum state observer. So if you are interested in this topic, you can read this paper. So when it comes to the sum state observer design for networked switch systems, actually in this IFAC conference paper, a kind of asynchronous sum state observer is proposed. However, it should be noted that event-triggered state estimation for switch systems with both synchronous and asynchronous switching remains an open problem. So the difference between this work and our work is that usually sum state observer, the sampling instant, it has a lower and upper bound, but the sample instant is not decided by ourselves. But in the event-triggered diagram, we will design an event-triggered mechanism to decide when to sample the output. So that's the main difference. And then we'll come to the second part. The third part is about the plant. So this is our plant. It's a switched linear systems. And X, U, Y represent the state input and output respectively. And sigma of T is the switching signal, which is a piecewise right continuous constant function. And we use TL sigma to stand for the switching time. And in this work, there is an average real time constraint. And TK notes the aperiodic sampling time, and which is generated by an event-triggered mechanism that we should design. So what's our goal? First, we consider a simple case, which means that the switch system's switching signal is synchronous with the observer's switching signal. And first, we use the sensor to measure the output of the system, and we design an event generator to decide when to sample the output, the continuous output, and transmit it to the remote observer. And the observer will use the input and output to estimate the continuous state. And in the second case, we consider a general case, which means that the system's switching signal may be asynchronous with the observer's switching signal. And but we assume that both the output and the switching signal can be measured. Both of them can be measured, and both of them will be transmitted through the network to the observer. And we will design the event generator to decide when to transmit them as well. And then the observer will estimate the system state. And finally, we will construct a kind of feedback controller to stabilize the switch system. So that's our main goal. And so in the first part, I will introduce you the multimode sum data observer. So it consists of these two parts. So in the first part, it's just a Lombok-like observer, but the difference is that since the continuous output is not accessible, so our basic idea is to construct an output predictor. So you can see from this equation, W of t is the output prediction. It has the same dynamics with the system output during the interevent interval. And at each sampling instant, which means the new sum output is accessible. So we can use it to reset the output predictor. And we use output prediction instead of the continuous output, y of t, because we can't access the continuous output to create the loop-like observer. So that's the basic idea. Besides, we also need to design an event trigger mechanism because we want to save communication and computing resources. So we designed the event trigger mechanism like in the inequality 4. So it means that only this condition is satisfied, the output will be sampled and transmitted to the observer. And in the left part of the inequality, it's EW of t. It stands for the output prediction error. And in the right part, it's EY of t. It represents output estimation error. And eta is a positive event trigger tuning parameter that we should design. So we have designed the event trigger mechanism. Then we can define the state estimation error as E of t. And we can obtain its aerodynamics, its equation 5. And then we can use Lyapunov method and average dwell time technique, average time switching technique to analyze the observation error system, its stability. So we have the first main theorem. It means that for these given parameters, and if there exist some matrices like this, and satisfy these LMIs, and also the average dwell time switch signal should satisfy this inequality, then we can say that the observation error system is GUS, which means globally uniformly exponential stable for this kind of switching signal. Besides, since we use a continuous event trigger mechanism, so we should rule out the Zeno phenomenon. So the basic idea is that first, according to theorem 1, the state estimation error E of t is GUS, so which means it is bounded. So we can so the following inequality always hold. And in the other hand, we assume that due to the precision of sensor, only when this condition is satisfied, the event trigger condition before can be detected. And the parameter rho is a small constant, small positive constant related to the sensor accuracy. So then we can prove the theorem 2. It shows that with the event trigger condition 4, and for any small positive constant rho, there exists a constant tau greater than 0, such that there exists a lower bound of the interevent intervals, which means we can rule out the Zeno phenomenon. So next, I will give you an illustrative example. We consider the following electronic circuit system. It has switching behaviors. It is composed of 2 subsystems, as you can see. And these are the parameters. So we let the parameters like this, And based on theorem 1, we can solve the RMIs through MATLAB, and we can calculate the feasible observer gains L1 and L2 like this. And also we can calculate the lower bound of the average dwell time this value. And for the simulation, we select the input as a sinusoidal signal, and we choose the initial conditions like this. And also we set the precision of sensor like this value. And then we can perform the simulation in MATLAB. And we choose a switching signal with average dwell time equals to 0.15, which satisfies the ADT constraint before. And then we can get the state trajectory and its estimation. So as we can see from the right figure, the estimated state can track the real state very well. And in this figure, it shows that the output. So the blue line is the continuous output, but we can't access the continuous output. We can only access the periodically sampled output y of tk. We can only access this sampled output. And also, we designed the event trigger mechanism to decide when to sample and transmit the output. And the blue line is the output estimation. The green line is the output prediction. And as we can see from the subfigure that the output prediction will be reset at each time that the new summed output is updated. Okay, so let's come to the second case. We consider a general scenario. In this case, the system output and the switching signal will be sampled and transmitted to the observer together. So we assume that both the output and the switching signal can be measured from the sensor side. And they will be sampled and transmitted to the observer. And we will design another event triggered mechanism to decide when to sample and transmit. However, the problem arises because, for example, during each inter-event interval, tk to tk plus 1, during each sample interval, there may be frequent switching during this interval. It may cause asynchronous switching phenomenon. It means that in this sample interval or inter-event interval, the system has switched several times. However, since in this interval, the sampled and transmitted information will not be updated. So the observer switching signal remains the same during this interval, which causes the asynchronous switching phenomenon. And we allow frequent switching during the inter-event interval. So the multimode sum-date observer designed before should become like this. So the only difference is that the switching signal of the observer, it becomes a sampled and hold version of the system switching signals, as you can see from this expression. And also, we need to modify the event triggered mechanism before, because we need to constrain the upper bound of asynchronous time in each inter-event interval, tk to tk plus 1. So we add another parameter h to constrain its upper bound of asynchronous time. So that's the main difference. We add another condition. And it should be noted that the parameter can be larger than the minimum dwell time. So which means that during each inter-event interval, there may exist multiple switching, which cause frequent asynchronous switching phenomenon. Besides, we have an assumption that we assume that each subsystem is stabilizable, which means that for every I belongs to the index state, there exists a control matrix K, such that this matrix is Hurwitz. And then we can design a feedback control law like this expression. And as we can see that the controller's switching signal, delta of t, is the same as the observer switching signal. It's different from the system switching signal, which means they may be synchronous. And also, we use the estimated state to stabilize the switch system. And then we can augment the system state x of t and the estimation error e of t. We can augment this two state as a new state, and we can calculate its aerodynamics like this. It's more complex. And then we can also use the output method and average dwell time switching technique to analyze the system's stability. And so we have the theorem 3 says that for these given parameters and also the control games satisfying assumption 1, if there exist matrices, these matrices such that the following 3 LMIs solvable, then the error system is GUES, globally uniformly exponential stable under assumption 1 for any average dwell time switching signal satisfying this inequality. So as we can see from the inequality 19, it's different from before the previous one, is that we have additional term, this term. It makes the allowable allowable lower bound of average dead time bigger than before. Okay, that's because there exists asynchronous switching phenomenon. Okay, so that's the difference. And also, similar to theorem 2, we can prove that there exists a positive lower bound of interevent intervals, which means we can rule out the Zeno phenomenon in this case as well. And next, I will show you the example. And it is also composed of two subsystems. And in this case, both the output and the switch signal will be sampled and transmitted through the network to the observer. And in that case, we concern the event-triggered observer-based control under asynchronous average dwell time switching. And we can select the parameters like this. And we can calculate the controller gains like this, K1, K2. And then from theorem 3, we can use the LMI toolbox to solve the observer gains. It's solvable. So we can obtain the observer gains L1 and L2. And also we can obtain the allowable lower bound of the average dwell time. And then we choose the initial states like this, the initial states of the system and the observer. And we choose the sensor accuracy as this value. And then we can perform the simulation. So it shows that the system converges to the origin, which means the system is stabilized. And meanwhile, we can see that the red line can track the blue line as well. And in this figure, we show that the switching signals of the system and observer. So the red line shows the switching signal of the system, and the blue line means the switching signal of the observer. So and sometimes they are asynchronous, they are not matched. And especially it should be noted that, for example, in this between these two sampling instances, or we can say that during this interevent interval, we can see that the system has switched twice. However, we can see from the blue line, the observer switching signal remains the same, so they are mismatched. And in our theorem, it allows frequent switching. It means it allows multiple switchings, more than one. We can our proposed work our proposed method still works. And the last figure shows that the event-triggered instance and the inter-event intervals. So as we can see from this figure, it's the sampling is aperiodic. It can save the communication resources. So that's the advantage of the event-triggered state estimation. So finally, let's draw a conclusion. So in this work, we propose a new multimode output predictor-based sum-date observer, which is used to reconstruct the continuous system state. And secondly, we co-design the observer games and the event-triggered mechanism, because we need to design the observer games and the parameter eta in the event-triggered mechanism. We co-design these two things, and it is based on linear matrix inequalities and average dwell time techniques. And finally, we consider both synchronous and frequent asynchronous switching scenarios. So the previous one is simple, and the later one is more complex and it's more practical. Besides, we establish sufficient GUES conditions for the estimation error system, and the simulation results validate our theory. And at last, I will introduce some ongoing works. The first work is about observer design for switched linear systems with sampled and delayed output. Because in this work, the transmission delay is omitted. We just analyze the observer design for event-triggered state estimation problem. We omit the transmission delay. So in one of our ongoing work, we also consider the aperiodically sampled and delayed output. And the second work is about, because in this work, in the second part of this work, we assume that both the output and the switching signal can be measured. But in this work, we extend. We assume that the switching signal is totally unknown. We can just measure the output. And then we need to analyze its observability and observer design problem for aperiodic sampled switched linear system. And this work, this is joint work with Professor Elena DeSantis at University of L'Aquila when I was a visiting student last year. Okay, so these are our ongoing works. Okay, thank you. That's all.
Thank you for the great talk, Zhaoyong. So maybe we can transition to the next speaker's presentation and take a question for Zhaoyong in the meantime, if we have one from the audience. Okay, if not, my question was actually about the fact that the switch signal is known in your observer.
Yeah.
So I guess you kind of answered that in your future work. So that's interesting. How maybe if you just have some sort of like basic approach on how you might do that. Do you have a very quick answer to that? Hello, can you hear me?
Yes, yes.
Oh, is there like a very basic answer you can give to that problem, like how you might approach when the switching signal is completely unknown to the observer?
Okay, so this is actually our ongoing work, and the key problem is that we need to distinguish the output belongs to which subsystem. So that's the key problem. We need to guarantee that the sampled output of each subsystem is distinguishable. Okay.
I see. Got it. Thank you very much. So we can transition to the next. We can transition to the next speaker now. So next up, we have Frederik Baymler Mathiesen. Hopefully, I pronounced that correctly. He is a PhD candidate at Delft University of Technology, working under the supervision of Luca Laurenti, and Simeon C. Calvert. Frederik received his MSc and BSc in computer science from Aalborg University in Denmark. He was a visiting student at UC Berkeley in spring of 2020. His work focuses on scalable verification methods, including synthesis methods for stochastic barrier functions, robust MDP-based abstraction methods, and bound propagation techniques for learning-based systems. So without any further ado, Frederik, please take it away.
Thanks so much. Yeah, so this presentation is going to be slightly different. It's going to be more tutorial-like over the subject of my PhD. So I'm going to present about formal verification of stochastic systems, both stochastic barrier functions and abstraction-based methods. So the context here is safety-critical systems, and as the name suggests, these safety-critical systems require strong assurances of safety prior to deployment. Examples include robotic systems in human environments, energy systems, medical appliances, financial markets, and many more where the impact of failure can range from significant financial losses and material damages to fatalities. My primary application domain is automated vehicles and more generally robotic systems, but what I'll present here today is more generally applicable to autonomous safety-critical systems. As a consequence of the high risk of failure, high severity failures, there's a strong desire to analyze and verify these systems using formal methods in the intersection between control theory and computer science. So to perform this verification, the procedure is typically that you first model some system, could be by first principles or system identification, and then you pick your favorite verification method and apply that. You get a guarantee with respect to the model. And the focus of this talk is just going to be on the verification method, but it's important to understand the context and impact of the choice of modeling. We can choose a high fidelity model with hundreds or tens or hundreds of state variables to represent some vehicle dynamics, but very, very few verification methods are actually capable of verifying properties over this model within the lifetime of this universe. Another consideration is whether the dynamics are stochastic or not. Typically, that's arising from environment variability. Now, with autonomous vehicles, automated vehicles, it's typically other road users, but also varying friction, wind, and other physical phenomena. And today I'll focus solely on stochastic discrete time dynamics. Before proceeding, it's important to highlight that the guarantees are with respect to the model, but we really want the guarantee with respect to the system. These methods can still give insights into the edge cases with respect to the original system, but this requires validation. There is an exception to this, and that's data-driven verification methods, and I'll come back to this point later. So these verification methods generally fall into two categories. They are stochastic barrier functions, which are similar to Lyapunov functions. You design a function to measure something under the dynamics of the system. In this case, we measure the unsafety level, do the conversion, get the safety level. And yeah, only look at the immediate dynamics and generalize that to a longer time horizon. The other approach is finite state abstractions, where you can construct a finite state model that relates to the original model in some capacity. You perform model checking. There are standard model checking tools for this. And because these systems are now related, these models are related, you can lift the guarantees from the abstract to the concrete model. Despite being seemingly very, very different, you can actually unify and compare them under the framework of dynamic programming. So before we proceed with describing these two families, I'm just going to formalize what we mean by safety and how it can be characterized using dynamic programming. So first, we assume some given autonomous dynamics. How you do the modeling is not the focus here, but autonomous discrete time stochastic dynamics with IID noise per time step. And then the probability of safety is the probability of staying in a given safe set for a given horizon at every single step. And then we have an infimum because we also have a set of initial states. So it's the worst case within this set of initial states. And that can be characterized via dynamic programming. So here we have a value function, vk, and at the first time step, it's the trivial measure. If you're in the unsafe set, it's unsafe. If you're in the safe set, you're golden. Then v1 would then be, if you're in the unsafe set, it's unsafe, you stop right there. But if it's in the safe set, you look at the expected value of V0 subject to the dynamics. So V1 represents the probability of being in the unsafe set or transitioning to the unsafe set in one time step. And you proceed this recursion until you get to Vk. So P safe is 1 minus Vk, again with the initial set. On the right here, you see a figure, an example of a one-dimensional system. And we start here at time step 10, because remember, we recursed backwards in time, and then gradually include more of the unsafety. The problem here is that this value function is over an uncountable space, so we can't just directly compute this, and that's where our two verification families come into play. With this in mind, we start with stochastic barrier functions. As I said before, they measure the unsafety level over a given set. And if you bound the expected increase of this function and you find the maximum value in the initial set, you can bound the expected value of this function after a fixed number of steps. And now if this value is, the level set we care about is b of x equal to 1, meaning that it's completely unsafe. That's in the black regions right here. Then if it's less than that, you can say that's the probability of unsafety in a fixed number of time steps. A little more formally, it's this function b here. It's a non-negative function. It's greater than 1 in the unsafe set. That just guarantees that the function is greater than the indicator for the unsafe set. Remember, that relates to the dynamic programming. Then we also bound the function within the initial set, and we bound the expected increase. That's the fourth condition right here. So let's look at some examples of what these functions could look like. If you have a constant function b of x equal to 1, that implies that gamma is equal to 1. And by our safety condition here in the blue box, we have that p safe is greater than 0. That's what we call a trivial certificate. Not very interesting. We want something different. The complete opposite is the indicator function, but the problem is near the boundary, it's very likely to transition to the unsafe set, and therefore the expected increase of the value here would be quite high. Therefore, you'd have a high beta, and once again, arrive very likely at a trivial certificate. So you want to balance this somehow subject to the dynamics. Now, we can prove that this safety guarantee is what you obtain via this dynamic programming. It is just proof by induction. You start with V0, that can be bounded by Vx very trivially. And because we have a bounded expected increase, we can bound each step. And then at the final step, we have Vk is bounded by Bx plus beta k. And with that, we can trivially bound P safe. But how do you construct these functions? Typically, you'd formulate this as an optimization problem. So the obvious choice is, let's turn to convex optimization. That's what's been done traditionally. There's quadratic, exponential, sum of squares. The quadratic and exponential templates only support linear dynamics, and they are a little inflexible due to the symmetry of their b of x equal to 1 level set. Sum of squares reduces this ever so slightly, but there are problems with scalability, and there are still some partial symmetries. Polynomials are super general, but sum of squares polynomials are a little more restricted. To understand what I mean by this symmetry and why it's important, let's look at this figure. Imagine this is a robotic systems. We have some obstacles, and we choose a reference frame where the center of the room is the 0 point. But then if we pick an exponential or quadratic barrier template, it has to be a rotated ellipsoid. And no matter what you do, the function will always be greater than 1 by the robot, which means that we've already designated it as unsafe right from the very first time step. So we want something that's a little more flexible, that can do more complex geometries. Of course, it's also important to pick the right reference frame, but if our function is flexible enough, that is less of a problem. So what do we pick here? We've gone to neural networks, done neural stochastic barrier functions. In this case, you train a neural network to be a barrier candidate and then post hoc do verification. In this case, we picked Crown. It's a state-of-the-art neural network verification tool. You construct these linear bounding functions, these green planes on the figure C. And then we do branch and bound. So if it's satisfied, great. If it's unsatisfied, great. If it's ambiguous, we continue to split until we reach a max volume, and there are some conditions there. But generally, the idea is that you rely on these bounding tools and compute whether it satisfies the conditions correctly. To train these neural barrier functions, it's a little tricky. Actually, it's rather hard because you really have to care about what your objectives are and your training techniques. So we've been relying on what's called adversarial training. So you rely on these linear bounding functions in Crown or interval bound propagation. Those are two options here on the right. And we also do curriculum learning, where we first minimize the safety parameters gamma and beta, and then gradually anneal it to satisfy the conditions that it's non-negative and it's greater than 1 in the unsafe set. That's necessary to properly maximize the safety bound we obtain. But another option where we go even simpler is piecewise constant barrier functions. We've been looking at this where it reduces to linear programming. We can also do a little bit faster, counterexample guided inductive synthesis based, or even a gradient descent approach. And in fact, we've also managed to prove that they are optimal in the sense that as the number of pieces grows to infinity, the bound we can obtain with these piecewise constant barrier functions is as good as any measurable stochastic barrier function. So great, but what we need to do here is to compute the transition probability or bounded transition probability from every region in the partition to every other region. And this can be interpreted as a sort of abstraction. And it kind of begs the question, why not just perform value iteration for all time steps over this abstraction? And in fact, it's a very, very good question, which also reveals the deficiencies of stochastic barrier functions for verification. For control, it can still be useful, but for verification, it has some limitations. The downfall here is that we bound the expected increase, which means over the sublevel set of b of x equal to 1, we pick the absolute worst case and look at that expected increase, which means that it's as if we're resetting the system to the absolute worst case at every single time step. And that's very limiting in the performance you can observe. It's not what happens with the real systems anyways, but the benefit is that you don't need to evolve these systems. So what is the alternative? That is this other family of finite state abstractions. The idea is that we construct a finite state model that in some sense contains the concrete model. So here, as an example, we take a region of the state space, partition it into regions, and each region is associated with an abstract state. So in this case, abstract state S11 corresponds to all the states in the region, or is related to all the states in the region in the top left corner. And then we got to design the transition system of this abstract model so that it contains all the behaviors of the concrete system. Then once we apply our verification tools, we guarantee that all the behavior, the lower bound for the abstract model also applies to the corresponding regions in the concrete model by this relation. So to do this, we start by picking our favorite model. What do we want to target? There are multiple options here. You can do an MDP. The problem is that you only have a single representative transition, so you most certainly need some kind of approximate relation, say the model mismatch of some capacity. The other alternative, what we've been focusing a lot on, is to do IMDPs, where you bound transition probabilities with an interval. Then you embed the abstraction error into this interval, and you guarantee that the corresponding transition probabilities are contained in the model. Most recently, I've been focusing a little more on factored IMDPs, where you deconstruct states into state variables. And the benefit here is that you reduce memory requirements. They can be a little bit faster as well. And an interesting side effect is that they do have stronger modeling capability. But that's not the focus here. You'll need to read the paper if you want to learn more about that. Now, the next step is to build this transition system in your abstract model. In this case, I'm focusing only on IMDPs, and the system we study here is a switched linear system, discrete time, with additive noise. The noise can be action dependent. So in this case, we have f of a, so the linearity of the dynamics, and g of a, linearity of the noise. In this case, for a given action, for a given source and destination, we first transform the source region under the linear transformation that is f of a, and then we pick the 2 points with the minimum and maximum probability of transitioning to our destination. We do that for every source pair. If you have actions, you do it also for all actions. But more generally, the principle is to find a transition bound. You often have to rely on some knowledge about the system. Can be linearity, or at least a certified first order Taylor expansion. Can be that you rely on additive noise. There's a lot of hacks, if you will, in constructing these abstractions, but it's doable. It's been done plenty of times. And then again, you apply your value iteration. As we saw before, safety can be characterized in terms of a value function. So model checking over these finite state models just amounts to doing value iteration. We start from an indicator function with SU, so the unsafe set or the avoid set. And for the recursion, it's the indicator function for the unsafe set. And if not in the unsafe set, we look at the expected value. And then we just do that a couple of times. The difference here to our original problem is that we have a finite set of states, so we can do this exactly. A benefit of this approach here of doing finite state abstractions is that we're guaranteed, as the number of states grows to infinity, that the verified probability that we get at our kth step correspond to or converge to the true safety value. The downside here is instead that the computational requirements grow kind of massively. The number of states grow exponentially with the original model, and the number of transitions grows even with the number of states more than linearly. But it does provide a stronger safety verification. So that's the basics of stochastic barrier functions and finite state abstractions. But what's the deal about these data-driven methods? Remember that the guarantees that we obtain are only with respect to our model of our system, but we really want it with respect to the original system. With data-driven methods, you rely on data from the original system, and you to at least some extent bypass the modeling, incorporate the samples directly into the verification, rely on some statistics. Because it's relies on sampling, there's at least some kind of formal confidence attached, and it can be a little conservative. But most importantly, you've got to be careful about your assumptions on sampling procedures. Can be independence, can be identical distributions across time steps, sampling axis, sampling from predetermined points. It's a thing that's very often misapplied, and is in the detail. I won't go into much more detail about it, but just to provide some references, you can use something like the scenario approach or conditional mean embeddings for stochastic barrier functions. And there's much more for abstractions, the Bayesian statistics, scenario approach, Clark-Pearson, Gaussian processes, Wasserstein, distances. There's a lot of stuff. So to conclude for a bit here, both of these methods obtain a sound safety bound. Both of them have been extended to more complex specifications of properties than safety, but they both still suffer from some limited scalability. Now, distinguishing factors are that stochastic barrier functions are conservative for verification, while finite state abstractions converge to the true value. That's not to say stochastic barrier functions don't have any value, because they can be very useful in control design, and you can design them using standard optimization tools, whereas finite state abstraction can really be computationally expensive, but they're also quite flexible. You can incorporate more knowledge about the original system and thereby do it faster and do something more strongly. And to finish this presentation, I want to initiate a little discussion here, because I'm thinking if we apply some of the, especially the neural barrier function techniques of these linear bounding planes and verification techniques, can we do value iteration or over-approximated value iteration of the original system without resorting to the finite abstraction? So we're ending a little bit in between a mix. I think that could be a very interesting thing to look at. Thanks so much.
Thank you for the great talk, Frederik. So I guess I can ask a question. Maybe we can see if there's any other questions from the audience. So you mentioned you had these piecewise constant stochastic barrier functions that you worked with in practice. And so if I understood correctly, these are sort of like, they take some sort of constant value on some constant set. So internally in the code, how do you represent this set pi, for example? Is this something that you can learn, or something that you can like sort of use some set representations of the literature? How do you get these PIs?
So now we've just been assuming that we are given a partitioning. You can try different partitionings. One thing we've also been looking at is to do it adaptively. So you start with a very coarse partitioning, and you only split whenever necessary. And you basically synthesize multiple barrier functions iteratively, but those barrier functions inform your choice of partitioning, if you will.
Gotcha.
Yeah.
Okay. Are there any questions from the audience? Otherwise, I do have another one I can ask. So then I think at the end you mentioned, again, about this neural network verification approach. So maybe if I didn't understand correctly, maybe it's something like you can use a neural network to learn not just the barrier function, but learn the value function itself. Is that kind of what you were getting at there?
Sorry, can you repeat that?
So I think right now your neural network based approach was sort of learning the barrier function.
Yeah.
If I'm understanding, and then you sort of do this verification approach after the fact to make sure that it is truly a barrier function.
Yeah.
Could you instead learn directly the value function and then somehow use some sort of optimization procedure to maybe verify, like in some neighborhoods or regions, that this is actually truly a value function? Or
yes, I think it's a very interesting thought. The challenge here is that you may need to adjust your entire function. Because we're dealing with formal verification, we care more about getting a lower bound for the probability of safety. So you need to do verification at every single time step for this value function, right?
Right.
You could perhaps condition it on the time step, but like there are some challenges here. But at the same time, I think it's very interesting, also because with these finite state abstractions, the biggest issue we're facing now is actually representing the value function, because the tables explode. It requires megabytes or gigabytes to store just the value function. Whereas like a neural network is a very good compact function approximator. So interesting.
Yeah, it kind of reminds me of some RL approaches where they sort of, I mean, you can go with this discrete approach of having a discrete value function, but somehow it grows in complexity. So I guess they somehow replace it with some sort of actor-critic-based method and go from there. So maybe that's applicable.
The bigger issue for using RL-like approaches for this is to get a formal bound. That's we want this to be a kind of a mathematical proof for the probability of safety, and that's very much still an open challenge of how to scale that.
Yep.
But yeah, we've also been looking in those directions for sure.
Cool. Are there any other questions from the audience? Okay, then with that, we can wrap up this seminar for today. Thank you both Frederik and Zhaoyong for giving some great presentations today. So our next one will be in 2 weeks. We'll have 2 more students / postdocs giving talks. So I will see you all there. Thank you again.
Thanks.